Hello everyone, my name is Miklós Svéd. I'm a product manager for Bricsys, and today I'm here to tell you about the new spaces and quick building features in BricsCAD BIM V21. So, as we know from philosophy of architecture, enclosing space is the ultimate essence and purpose of architecture. So, what a humbling task it is for a software designer to have the opportunity to work to design spaces for a new generation BIM software. So the requirement of this development task was to implement the concept of architectural space and building mass in BricsCAD BIM. And we also know that massing, how important it is for the building. From the inside there is the space which we need to protect from the external elements, but the shape of the space also shows in the outside of the architecture. So they are connected, and that is why the concept of space is closely connected to the concept of building mass. Spatial information is important for many stakeholders that work with the building throughout its life cycle. Architects, for example, look for floor area and function of space or room, whether it's a living room or an office, and they display this data on the design documentation, and they also, of course, list it in the room list. MEP engineers, they work with slightly different information that is related to spaces. So they look for volume and occupancy, which will help them with their thermal load calculations, which is necessary to size the building systems. Contractors, on the other hand, they look for the surface area that cover the spaces to be able to quantify the surface finishes that they need to purchase and install during the construction. And finally, during the operation of the building, facility managers, they work with data such as rentable area, cleaning area, space containment, to be able to efficiently handle tenant and asset management. So, consequently, we can say that spatial elements must become the backbone of a new generation BIM software. So that's on the side of the requirement. Let's see how we went about with the implementation. So our solution introduces the spatial elements in a hierarchical order. You'll see that we have the building, the stories and the spaces, spatial elements, which are ordered in a tree-like structure in line with the IFC definition of spatial element hierarchy. And they're integrated, of course, with other BIM model elements in the overall BIM model. So what are the benefits of this approach? First of all, we have full freedom to model spatial geometries, just like how we have the full freedom to model any building element in BricsCAD BIM. Also, we can retain the parametricity of our 3D solids, which in this case are applied to model spatial geometries, and we can enjoy the full direct modeling capabilities that BricsCAD BIM is famous for. That's the model object part of the spatial element implementation. The data part is solved by data containers, which are linked with the 3D spatial elements, and they contain metadata which can be either according to IFC standards or customized to suit the particular need of the user. These parallel spatial definitions that you see on the screen are quite unique to BricsCAD BIM, because in our software it's possible to have multiple representations to show or to represent the same spatial elements. So here you see a space, a simple room with its simple 2D geometry, with its complex 3D geometry, which captures the exact volume required by engineering. And then there are abstract representations which are used for standard specific calculations, such as the area calculation for office buildings used in the United States, also known as the BOMA standard. So here we can use 3D volumes or 2D abstract shapes to represent our building spaces, and they can all be combined and live together in the BIM model. So after this introduction to spatial elements in general, let's take a look at them one by one. First of all, the building spatial element, which is to be used, for example, for preliminary building design, also known as massing, and the evaluation of the design with respect to building regulations. So this geometry already contains a lot of information that we can harvest from it, such as total floor area, building footprint, and we can relate this data with other model element data to derive further information, for example, lot coverage, lot to building ratios such as floor area ratio, floor space index, or building coverage ratio. These are all very important metrics in the early stage of the design to be able to make informed decisions regarding which design variant is the best, which satisfies the requirements the best possible way. Going further, we can also use these building spatial elements to display the geometry of the existing neighboring buildings of a design project. And so these are usually low LOD representations that give the setting for our more deeply elaborated design. And there's also a good use case to use the building spatial element to share the geometry and the metadata of the designed building in a low LOD with external applications such as GIS apps or the city database. So that's it for the building spatial element for an introduction, and now let's discuss the story spatial element, which can be used to record the division of the building volume into stories, how you see on the right upper side of this slide. This way we increase the LOD and are able to provide information regarding the usable floor area of the building, total floor area built, floor area ratio, floor space index. These are also important metrics. And finally, we arrive to spaces, which are the most detailed representations of spatial elements in the project. And it is there to maintain the architectural roof information about the occupied areas and service other disciplines such as MEP engineers and contractors or facility managers, as we already discussed earlier. As the next chapter of today's demonstration, let me show you some of the features of the BricsCAD BIM V21 spatial elements. First of all, let me show you how you can create spaces. There are two ways to create spaces. One way is to just QuickDraw. I QuickDraw here 4 walls just for demonstration purposes, and you can use the space tool to place a spatial element, a space, very easily. By default, it shows up with a footprint representation, which is one of the representation options for spaces, but you can toggle it to a solid representation as well. Then the next thing I would like to illustrate here, if we grab this space and come up with the, or enter the BIMSpace command, then the bounding elements of this space are highlighted. So you see there are indeed 5 bounding elements that bound this space, these 4 walls and the slab. So it is possible, these were detected automatically. So the condition for the software to automatically pick up the bounding elements upon space creation is that the property of the element of the bounding element, space bounding property, should be turned on. In this case, the space will be created as it is bound by that particular element. And then, as I showed you already, we can use the BIMSpace command to pick up these elements, and then you can add or remove bounding elements from the space. So this way you can control the bounding elements manually as well, which becomes very important, especially when you work with more complex spaces. Another way to create spaces is to just start with any primitive and then use classify space, and then you can turn any solid into a space, and from that point on you can freely play around with its shape to create more complex spatial geometries. For example, in case of auditoriums or large exhibition areas or sports facilities, the geometry complexity of the spatial elements quickly grow beyond the cubes. So in that case you can work on these spaces manually to achieve any shape, and then of course you can assign bounding elements to it. So let's say this is a wall, and its space bounding is set to on. Then we go for BIMSpace and edit, and decide to add this wall element as space bounding element to this space, and then from that point on the connection is established, and you see that the space indeed picks up its bounding element. As a next exercise, let's see what happens if we push-pull the bounding geometry a little bit. First of all, let's observe the status of this space. It is up to date, it aligns perfectly with the bounding elements, but now I will temporarily hide them. Grab one of the bounding elements and move it sideways a little bit, making sure with the help of the control switcher that the other adjoining elements move along with it. So I just make the host room a bit bigger, and when I turn on the visibility of the space, you see that the space didn't follow this change, but the status indicator changed through to out of date from up to date. And the technology behind this is that there is a connection established between the space and its bounding elements by the means of reactor mechanisms, and the space knows about changes made to its bounding elements. So and notifies the user that indeed update is necessary. So in this case we just type in BIM update space, and voila, the space is automatically updated, given that the update method is set to automatic, and you see that the status has changed to up to date. Okay, we keep on working on the geometry of our building, and maybe at one point we decide to add some suspended ceiling that changes the volume of the space. I will just model that real quick. Use the polyline to draft some random outline for the purpose of the demo. And then grab this region and extrude it inwards. Maybe there's a change in the ceiling level there. So you see that now, as I started to manually edit the space, the update method automatically switched to manual. Now in this case, spaces that have update method set to manual, they cannot be updated by BIM update space. So if I key in BIM update space again and try to do the update, you see that indeed the space has been skipped because it is manual. The reason for this is to avoid data loss or data distortion. The work users put in to modify and enhance the geometrical complexity of their spaces should not be lost by some random batch update of spaces further down the line. So in order to avoid that, we implemented this update lock. Now what happens if you do want to automatically update this space anyway? All you need to do is to switch the update method to automatic and run BIM update space again, and for some reason it didn't change. Maybe I did something wrong, but I will try once more, and there you see now BIM update space works perfectly fine with the space set to update method automatic. You see that the additional geometry has disappeared and the space lines up with the bounding elements as before. So that's how the update lock mechanism works. After the chapter detailing the features, let's move on to the workflows. I will demonstrate 3 different authoring workflows which enable the creation of spatial elements. First of all, an import from IFC into BricsCAD BIM. Thereafter, a top-down generative building design workflow, which is an example of the QuickBuilding functionality. And finally, another variant of QuickBuilding, which is a bottom-up program-based building design workflow. Let's open up the example file. It's an actual project. You see that the model in its present state consists of unclassified entities and some block references. So we need to run BIMify on it, which does a whole bunch of things. It classifies all model elements and adds spatial information, creates spaces and sections, so it turns the unclassified solid model into a full-fledged intelligent BIM model. Let's see how it's done. Actually, BIMify is not only one action, it's a series of actions. The software walks through the model and analyzes, categorizes, and adds data to the model elements. That's why it takes some time for this to run, but the end result will be worth the wait. Meanwhile, we see that the solids representing spaces are added, and that's it. We're done. If we just hide some elements to make it look more simple, we see the large number of spaces that has been automatically created by BIMify, and we could hover over to one of the more complex outlines and see that the detection was flawless in case of even more complicated geometries. You can use the existing and already mentioned features, the representation feature, to view or visualize the spaces as solids, or you can toggle that to footprint, which is a 2D representation, whichever is more convenient. That's it for the first example of automatic space creation based on a set of existing bounding elements as part of the BIMify framework. The second workflow I would like to show you displays the new QuickBuilding feature in action. QuickBuilding is a generative building element authoring tool which relies on artificial intelligence to turn a solid into a full-fledged BIM model. So for that, the input is just any kind of solid. I'm using this strange shape, and you see that this is just a bunch of solid entities, so no BIM data added at this point. So let's key in the BIM QuickBuilding command, select the solids that we want processed, and now we are presented with two choices. Basically, the options here are whether we want this input solid processed top down or bottom up. I will first show you how top down works on this model. So I will just say that let's treat this input solid as if it was a building. The next question we need to answer is the story height. There are several ways to enter story height. You can enter it via a building requirement file or through the Spatial Locations Manager dialog, or via direct input using the command line. I will choose the latter for simplicity's sake and enter a uniform story height of 4 meters. By the way, you can enter several different, a combination of different story heights. If you have different story height in the underground garage than on the ground floor versus the floors above it, there's a way to enter a variation of inputs. Now I work with the 4 meter input, and the resultant model has already been generated. Let's explore the model. First of all, let's look at the spatial elements generated by QuickBuilding. To be able to do that, I hide the building elements, and then I will hide all elements but the building spatial element. So here you see that the input solid has been turned into a building spatial element, which carries all the metadata of the building. And you see here the building represented with the spatial element solid. Now the next thing I want to show is the stories, which are also generated based on the story settings and the original shape of the solid. You see here the different stories have been generated by the software automatically. So after investigating the spatial elements that were generated, let's look at the building elements created by QuickBuilding algorithm. So to do that, I first hide the spatial elements and then show the building elements and cut a random section through it. Show that section to you. And as I position the section plane, you can see this intricate geometry of the original building solid turned into a full-fledged BIM model, meaning that there are walls, slabs and roofs generated. If we look at the model, it's quite complex already, and imagine we started from a simple input volume that can be easily created manually or with the help of some generative tools such as Grasshopper, as you will see an example of that later. Right now I just want to draw your attention to the fact that before QuickBuilding, users of BIM software had to draft such geometry manually if they wanted to have an informed decision regarding, for example, the total floor area usable in this project. Now we can obtain this by click of a button. So now let's visualize the entire model again. And look at the different building elements in an isolated way. First of all, I will show you only the walls, and then I will show you roofs and slabs, which are color coded for convenience sake. You see the internal slabs are colored red, the external slabs which face the bottom are colored gray, and by the way, they are also placed on different layers. So if you go here on the layer setting, or the setting or the properties of this element, you see that is on the external slab layer, while the other part of this same, the continuation of this same slab, which is inside, it is on the internal slab layer. So all these layers necessary to differentiate between the different generated building elements based on their position within the model relative to one another. These are created automatically, and the corresponding elements are placed there automatically as well. So for example, if we look at the roofs in an isolated way, we see the intricate roof geometries climbing up these two spirals. Just imagine if you had to construct that manually, how long it would take. So now we can see that the building elements and the freshly generated spatial elements live side by side inside this BIM model, which was automatically generated based on input solid. Let's recap that, look at the slide that once again summarizes what happened. So for example, let's say we place urban scale study in an existing city model environment, and want to have some BIM related information about this design. Then we isolate this building mass, which is just the same level of detail as any other low level of detail city building representation, or building representation on the city scale. And then we simply activate the QuickBuilding, which generates spatial elements, buildings, spatial elements, stories, and all the building elements, walls, slabs, and roofs automatically. The third spatial and building element authoring automated workflow I would like to share with you is another variation on the QuickBuilding command. This time it's a bottom-up program-based building design workflow. The slide will show you how to put the input solid together for the bottom-up QuickBuilding. Here we could start from architectural building design program, which lists the necessary spaces of the project and the adjacency information, meaning which space should be adjacent to what. In this very simple schematic example building, we see that there's a traffic area facilitating vertical traffic in the building. It's entrance. It's connected to a lobby or to an entrance area on every floor, and from this area further spaces open on each floor, and these are structured in sort of a hierarchical order based on their adjacency, based on their connection patterns. So this is how architects lay out a floor plan. In many cases, you just draft a floor plan, making sure that the spaces connect the proper way and each are sufficiently sized. The next step of this workflow would be to turn these 2D schematic floor plan polygons into 3D input solids. So it's rather easy to just extrude them to the story height, and then you have the arrangement of the spaces within the story of the building. Then you can go forward and stack the stories one on top of the other to get the final input solid that represents the space, the net the gross spaces of the building. Here we must explain the difference between the gross and net space concepts. So gross space is a spatial representation which also contains the building elements. So the rooms here, or the spaces they touch, there is no walls or slabs yet, while net spaces, they don't contain the spatial element, don't contain the building element volumes. So in case of net spaces, there are indeed gaps between the spaces. So here we work with gross spaces and use those as input for the bottom-up QuickBuilding. So after the slide, let's see an example building, this time a small residential building where you see the 3D stories with the gross space representations, meaning that there are no gaps between the spaces, only these solids representing the gross spaces. And let's see what the QuickBuilding algorithm does with such an object. So I just start QuickBuilding and once again select the solids to be quick built. Now we are facing again the selection whether we want quick building to work top down or bottom up. We already saw an example of the top down approach, so let's use the bottom up workflow now and look at the input solids as if they were indeed gross spaces. Now the quick building process has started, and the result will be generated in a new file. So the original input file is retained, and a new file has been created to show the resultant BIM model. Let's once again see the spatial elements first. First of all, I will hide the stories and look at the building representation, which is indeed a building type object now, spatial element with all the bells and whistles of the building spatial element. And if I go further and show the story structure, you see that there are indeed spaces generated on 3 different stories, and these spaces are net spaces, so the gap between the spaces are visible where the building elements are fitted. So we can of course toggle the representation of these spaces from footprint to solid to have a better view of the net spaces generated by the quick building algorithm. So with that done, let's turn our attention to the building elements, cut a section to see the structure. You see that indeed the model has been created, and if we look at another section, this time to show the floor plan, we see that the internal and external walls have been generated and positioned automatically by the software onto their relevant layer, and so we end up with a pretty decent BIM model. If we import the surroundings, then we could combine the generated building with the surrounding environment to get a even more accurate representation showing the different stories or sections as well. Mind you that this intricate BIM model has been generated based on just a number of solid shapes, and we ended up with a model which I will show you that of course now it's time to further elaborate the design with the direct modeling and other tools that BricsCAD has to offer, and so this way we can achieve a rather detailed BIM model, which at the end of the day will look like the example building. How to get here is basically you need to use propagate or manually add some windows, and you can use auto match to add compositions, and at the end of the day you can come up, or the end result can be a BIM model ready to be quantified in terms of finding out how much building materials you need to build this building, and to stick a price tag on the price for the building construction elements. So that is what I wanted to show you in terms of the bottom-up quick building. Let's quickly recap and summarize using a slide what happened. In case of the bottom-up approach, you start from the architectural building program and draft the 2D floor plan, which then you can extrude into a 3D floor plan of a story. You stack the stories to get the input solids, which then you run through quick building, and the result is the spatial elements in a hierarchical order, and of course the generated building elements. As the next chapter of the demonstration, let's speak a few words about interoperability, how you can communicate spatial elements to third-party applications back and forth from BricsCAD BIM V21. First of all, you saw that the volume representations of the spaces are just what engineers and building performance evaluation experts need to run their studies regarding energy performance or smoke and fire, acoustics, egress, you name it. All these applications look for space volumes for input. And of course we can serve this up to them in convenient formats of DWG or IFC. We can do the same with the facility management software. We can perhaps reduce the complexity of the spatial representations before we communicate the data to FM software. Same is true for urban planning apps. Usually in that case the level of detail is relatively low because many buildings need to be shown all at once. So then we can grab the building spatial element, which is a low LOD representation that is part of the potentially very detailed BIM model. But we can grab the simple representation and communicate it towards the urban planning applications. We can, of course, also use quick building to drive quick building or drive BricsCAD BIM through quick building with program-based design applications or generative design applications. So there are already program-based design apps for Grasshopper, which serve up a number of different layout variations based on building design program as input. We did the same manually, remember, in the bottom-up presentation of quick building, but there are apps that automate that. And in the same way, you can use generative applications to connect to the top-down quick building. For example, here is an example how to use Grasshopper to generate a number of design variations and evaluate those using top-down quick building. On the screen here you see an urban area with a red building in the middle being changed with the help of Grasshopper, which appears on the right side of the screen. You see the visual script of the building solid. It's being manipulated. Once milestone has been reached, we can isolate and quick build this variation and harvest lot of useful information, for example, footprint area or floor areas, as well as quantified building elements based on the original shape generated by with the help of Grasshopper. Then we can go back to the original design and iterate further using both direct modeling and Grasshopper. The sliders in the Grasshopper, for example, just changed the height of the building now, and we also changed the outline of the building by changing the input polygon. Now we quick build the second version that will result in a slightly reduced footprint area. Now we go back to the original design and use the remaining two sliders to tilt the facades and increase the internal atrium, which results in perhaps the most exciting shape, but with the least amount of usable floor space area. But let's not guess, but rather compute and calculate. Use QuickBuilding to build this third BIM model as well, and base our decision which one to further elaborate on the scientific data that's been generated with the aid of artificial intelligence that is embedded in BricsCAD BIM V21. You see that now the three variations of the BIM are X-referenced back into the urban contexts. Let me use this slide, which shows a different building in a different context, but shows you how these design variations can be put together side by side with their geometrical representation and their key metrics such as floor area ratio, floor space index, and building coverage ratio, as well as floor to side ratio. All this data can be harvested from the quick build BIM models, and this way we can have an informed decision which design variation to pick and carry further. So that brings us to the end of our presentation that was showing you the spaces and quick building functionality in BricsCAD BIM V21. Let's summarize the contents of the demonstration quickly. First of all, the requirement was to implement the concepts of architectural space and building mass in BricsCAD BIM. So our solution involves the use of 3D DWG spatial elements called building, story, and space in a hierarchical IFC-compatible data structure. We saw that there are several quite unique and powerful features such as full space bounding element control, solid or space or spatial representation option, automated or manual update methods, status control, and the update lock, which will avoid data loss or data distortion throughout the authoring process. We looked at a few different workflows, how we work and generate and modify and author spatial elements. For example, the building element based BIMSpace authoring, where we automatically just place the spaces based on their bounding elements. We saw how spatial elements can be freely modeled to achieve virtually any geometry while still maintaining connection with their bounding elements. We saw several examples of how to generate building designs top-down or bottom-up based on a program, of architectural design program. And finally, we saw how all this technology allows us to carry out comparative analysis of design variations in a very early design phase in an almost fully automated way. I hope you enjoyed today's demonstration, and we look forward to you trying our software soon. Thank you very much.